Okay, so tonight's presentation is Semiconductor Quality Assurance through Metrology, and we do have a panel discussion with speakers Dr. Andy Wong, Dr. Carlo Da Cunha, and Dr. Miguel Jose Yacaman. And the panel is going to be moderated by Lauren Major. So I'll go ahead and introduce you both, give the background really quick that I gave previously for all of those rejoining us. So Dr. Andy Wong is professor and director of the Metrology Research and Teaching Laboratory at Northern Arizona University. Dr. Carlo Da Cunha is an assistant professor at the School of Informatics, Computing, and Cyber Systems at Northern Arizona University. His research focuses on an interplay between quantum science and machine learning. And Dr. Miguel Jose Yacaman is Regents Professor of the Applied and Material Science Department at Northern Arizona University. His research has been on materials characterization using electron microscopy. And with that, I will give the floor to the four of you.
I'm going to jump in right now real quick, Hillary, and just introduce myself real quickly. I'm Lauren Major, and I'm with Workforce Development with the College of Engineering, Informatics, and Applied Scientists. And I'm going to be asking the questions. You may have ascertained that I am not the engineer here, so we're gonna let faculty answer those questions. But this is all related around a grant that we were recently awarded that Andy had mentioned from the ACA. And it was funded to help expand and enhance our metrology training and education. And so that's where our discussion is going to go today. And I'm going to start with the first question, and that would be, why is metrology important for semiconductor? And I think, Miguel, I'm going to start with you.
Okay. Okay, so let me share I would like to share my presentation.
Of course, let me enable it. I'll stop my share and then
okay. Okay.
So just a second. Okay, now you should be able to share.
Let me just close some windows so I don't get confused. Okay. Okay, so share. Okay. Okay, what I'm going to just discuss, you know, there is a report by the National Institute of Standards and Technology, the NIST, who says that one of the key points on development electronic industry microchips is basically related to metrology. The metrology has to set standards and has to make things important. I mean, this is a way to characterize, to really assure quality control. Okay. So it's a key part of all the manufacturing of the electronic industry. And I would like to mention that there are three different levels of metrology. The low end, that we call low end, means that we're looking at things of millimeters, centimeters probably, and we do it with an optical microscope or other means. And that's a first step of quality control. In a second step, we go to the micro level, which is only a few microns the size. And there are two techniques which are used, scanning electron microscope and secondary ion mass spectroscopy, which is used to get the chemical analysis of the sample. However, there is a high-end part, which is when you are going to look for nanometers samples, okay? And that is what we call high-end, and I'm going to talk only on the high-end part because this is where at least my participation on this will be focused. And of course, the program of Dr. Wang is mentioning will cover the three areas. Okay. So I would like to say that in the high-end microscopy, I mean metrology, there are two microscopes who have been transforming completely the field, and they are going to have the most impact. One of them is the transmission electron microscopy, with what is called 4D stem. Okay, and I will explain what is this. And the other one is what is called dual focus ion beam plasma, with use of plasma. Okay. We have the instrument in the left is in NAU, and this instrument in the right will be located on the North Valley campus of NAU to be close to the industry and probably the possibility of either moving or buying another electron microscope. So let me start with the first. I guess the big problem of metrology is, for instance, the sample preparation. How do you prepare the sample preparation? How do you prepare the sample? Second, now the microchips now are three-dimensional. And when you analyze it, you have to go layer by layer, and you have to delayer the thing to prove the new microchip. The next one is the strain measurements, because if you have a strain in the interfaces between semiconductors, that introduces a malfunction and, in fact, it seriously limits the performance. And then, of course, you have, electric fault insulation, and finally, accurate size determination. And the size is very important, and you were talking about smaller and smaller, and then the accuracy of the measurement has to be done. Okay. Let me just take the sample preparation very quickly. What you do is you take the microchip, and then you use an ion beam to polish the material. Here is the picture when you see the sample who has been thinned to be seen in the electron microscope. And basically, they use a gallium beam, ion beam that produce the tip. The problem with that is that you introduce a lot of radiation damage. In the surface, and the people clean the surface afterwards. However, there are still ions of gallium that go inside the semiconductor. So sometimes you are not very sure if you are seeing things were related to the radiation damage. However, and I just want to say that I already said that the microchips now are three-dimensional and smaller, okay? And then you have to be even more smaller in the characterization. Well, the way to do is to use plasma focus ion beam. In that case, instead of using the gallium beam, you use a plasma, a plasma from a helium or another gas. And then the milling is very, very gentle, no radiation damage. And then your sample represents much more what it really has to be. Okay, and then you can see that then you can go to using the same instrument, the focus ion beam, to test small parts of the microprocessor. Okay, you can even do some measurements at this scale, and you can even go to detect, thermal failure or check the connections in this. Okay. Now, by the way, I have to say that this focus ion beam, it also will have a low temperature, really cryogenic, and that has produced a tremendous revolution in biology. Now, all the biologists are really making tremendous advances using the tomography techniques with electron microscopy. Probably the most significant was that when the COVID came, in the matter of 1 month, electron microscopy has developed, has studied the S protein, and that was the basis of the vaccine. And what happens is, in the background, you see the regular image, and after you do a tomographic reconstruction with it, this is what you see. You see three-dimensional, and you see that's why it has been tremendously important for many. Semiconductor industry has not discovered yet this facility, but it will, because it's very important. Okay, the next instrument I would like to mention is the transmission electron microscope. Well, what happens is that after almost 70 years of his discovery of the fabrication, electron microscopy achieved the goal of seeing atoms, okay? Now we can see routinely atoms, and If you've never seen an atom, this is a picture in which every bright dot is an atom. And then you can see even some distortions on the way the atoms are located. And the resolution that we have is 50 picometers, below 1 Angstrom, okay? And also, you can see atoms all the time. This is a very routine now to see atoms. And in addition, there is a technique called scanning transmission electron microscopy, in which the images depend upon the atomic number. So if I go back in this picture, you can see a very bright spot, which is one specimen, and the other weak atoms are another atom. And if you do the calculation, you can calculate which atom is which. Okay, so it's kind of chemical analysis. But now the big difference is now what is called four-dimensional STEM, in which you have a pixelated detector, and then you really probe the sample three-dimensional. Okay, so you make a three-dimensional map of the sample, and that is one of the big advances now in electron microscopy. And let me just mention the first problem: strain. When let's say assume that you have a device which is silicon, germanium, silicon, etc., you are going to have different spacing in the interfaces, lattice spacing. So you have a strain. The strain, if you have interface dislocations, you are screwed. You have to have a strain without dislocation. Now you have to measure the strain. Is how much the lattice expands. Okay, an electron microscopy can determine very easily. And this is an example of a multi-layer quantum well structure of gallium arsenide, an aluminum arsenide, and then you have the layers deposited in different thicknesses. Okay, this is what it looks. I believe this is a optical device, probably a lead. Okay. Now, when you do electron microscopy, you see the atoms directly. You see the structure through diffraction. And then by measuring the space between atoms, you can determine strain. And this is a map. You can see below, yellow means a lot of expansion. Blue means a lot of contraction. And when you compare, for instance, you see this interface corresponds to this. This interface is okay because it's more or less in the center. But the other one, the green one, is not. There's a lot of compression here and a lot of compression in the other. So that's an example of how you can control the quality of your device. And now with the 4D STEM, people are plotting in 3 dimensions the strain. And this is a great thing because you can really get much more information. Okay. The other one is chemical analysis. This is an example of a device. I believe it's a MEM resistor produced by Dr. Cambu in NAU. You make a thin with the focus ion beam, and then you do electron microscopy. And if I want to know what is in here, I can do chemical analysis. And you know, I can detect that whether this is, for instance, aluminum, titanium, nickel, and so on. And now the analysis has become so accurate that we can go atom by atom. This is an example of an alloy in which copper has precipitated in a grain boundary. We can analyze atom by atom chemically. And by the way, Richard Feynman, in a very famous paper, said that in the future we will be able to analyze chemical atoms one by one. Now, finally, we are in that front, which is very good. Okay. Now, I would like to just say why it's important, and I'm sorry I took all this to get to the point. Why is so important the quality control and the metrology? Well, as you know, Taiwan Semiconductors is in the course to produce 1 nanometer monolithic chips with 200 billion transistors. Okay. So now the industry is producing 14 nanometers, 7 nanometers. This is more or less the standard. Now their production, the 3 nanometers has been demonstrated, and the 1 nanometer is in the make. Okay, people predict, depends upon that, probably within 3 or 4 years will be in the rate on that. Now, the problem is if you see, this was an announcement of Taiwan Semiconductors about this technology, and they are using bismuth for a contact electrode, which is absolutely important. But they produce the bismuth using a helium ion beam lithography system. Like the one we're going to fab or system will have lithography with the ion beam. So that's an example how this instrument is very important. And we hope that. And then also, if you see, they are using what is called two-dimensional materials that a few years ago they were purely for the academia and now are really being used, including molybdenum disulfide and tungsten disulfide. And this is an image of the paper that was produced by Taiwan Semiconductor researchers and MIT of a 1 millimeter material. And you see, you have to higher K material like hafnium oxide. But this is the silicon, okay? This is the silicon. But then you have to have another material, which is, let's say, another electric contact, okay? Or in this case, it's a two-dimensional material. And just let me tell you how you have to be very accurate to do this measurement, and only the electron microscope can do it. And let me tell you, in the case of molybdenum disulfide, it's a very peculiar material because it comes in layers. To use it in the electrodes, you have to delayer and produce individual layers of 1 or 3 layers. This material is like a sandwich in which the bread is molybdenum and the ham is sulfur, and it comes in layers, okay? And it's so delicate that the numbers of layers determine whether it's a semiconductor or a metal. For instance, the phase, what is called 1T, which is made only of 2 monolayers, is a metal. If you add another monolayer, it becomes a semiconductor, okay? And in fact, one of the things we have discovered in the group is by measuring the electric conductivity of a molybdenum disulfide wire, this will be the typical graph for a semiconductor. We are doing current versus voltage. So the graph is non-linear. But if we bend the nanowire, it becomes metallic. Okay. So that tells you the degree of precision that we have to be to control where you are putting it. Okay. So in conclusion, I believe that now that we're going to the 1 nanometer realm, the really characterization at the top level becomes very important. And we hope that NAU in the center is going to establish in the North Valley campus of NAU will help the electronic industry to do not only characterization, but also joint research in developing these things, because we cannot say that the problem is resolved. But just imagine if we really produce reliable 1 nanometer chips, it's going to be revolutionary. And that's what I would like to say.
Thanks, Miguel. I want to remind everyone, if you have a question, feel free to, we do have a hand raised there. Samet, do you want to go ahead and unmute and ask your question? Okay, not there, sorry. All right, we're gonna move on. And this is kind of important to tie in the last thing that Miguel said about NAU. And so, Andy, can you tell us how NAU can support metrology training with all the new programs that we have coming up?
Sure. I'd like to first of all add just one sentence on top of what Dr. Yakman mentioned. As we make the chip smaller and smaller, I mean, metrology is becoming more and more important. And you take the 14 nanometers chip manufacturing, for instance, totally there was 1,800 steps. And roughly there are about 20 to 25% of that 1,800 steps related with measurement, related with quality control, related with metrology. So that's very, very important. Dr. Yakman also mentioned that TSMC is doing research on the 1 nanometers. And we all know TSMC originally they want to build one fab. Now they are building second and the third fab, and they are going to produce 4 nanometers FinFET chip in 2025, right? Originally it's this year, but they postponed 1 year, 2025. But in 2028, they are going to produce here in Arizona. They're going to produce a 2 nanometers chip. Right? So that is really require a really high profile metrology equipment like a FIB, like a TM, like other equipment. So we are going to use the chip money, the $30 million investment, and put some of the equipment in our North Valley campus. Some of you might know NAU has a North Valley campus, which is right off the Interstate 17. It's a Greenway Road, exit 211, I believe, on Interstate. It's only 30 miles from TSMC, about 25 miles from Intel Chandler fab location. So we welcome the industry partners with us. I mean, we buy equipment, we put it there. We don't want those equipment sleeping there. Nobody use it, right? We like to share with industry and share that expensive resources. Now, on the education side, we're going to create a certificate program for our degree seeking students. If you are EE students, for instance, you take this certificate, a few courses, and then it's add on top of your degree. Also, we are reaching out to high school CTE program and create a registered apprenticeship program with them. And we encourage our students take interns, take a core, take a practical experience with industry partners. So the grant we receive, the grant project, will cover both research and education. So research side is what Dr. Yakman mentioned. We are doing the research with different industry partners. We are creating a number of proposals with RISIAN, with other industries, and that is a part of the grant. Another huge part is education. So basically, we want to build a career path to engineer, to technician. So the first registered apprenticeship program is a calibration technician, right? So it's but anyway, why we're doing this? I mean, based on my experience, engineering education need a reform. Okay, we emphasize design, but not on the quality control or the metrology part. I strongly believe engineering curriculum need reform a little bit, revise the curriculum so that we emphasize both design and the metrology quality part. So that is partially our goal for this grant project. Thank you.
Andy, do you want to talk a little bit about the quality control issues in the semiconductor industry workshop?
Oh,
that we're
yes.
hosting?
Right. July 25 to 26, we have 2 days. We invite everyone interested to join us this summer. Flagstaff summer is beautiful. It's cool here. July 25, 26, come here. We have a TM workshop. Focus on what Dr. Yakman just talked about. How do we use the TM, STM, those kind of transmission electron microscopy to do quality control, to analyze the sample data and improve our quality for semiconductor. So that is a very short commercial for this for this workshop. Please, Lauren can share more information about that workshop.
Yeah, I'll put my email in the chat, and anyone who has any interests, please go ahead and feel free to send me an email and I will share those details with you.
And I just say that it's going to be hands-on workshop, so people will use the instruments.
Okay. Our next question here, and maybe I can expand a little bit too on the training programs. We are very excited about doing a registered apprenticeship program. So that means that it is sanctioned by the state, And our first one is going to be for calibration technicians. And so if that is something that anyone has an interest in as well, again, go ahead and email me at the email address I just posted. Okay, we're going to move on to the next question. And what are the limitations of conventional metrology?
But the size, as for me, the question, I guess, is the problem of the size, okay? An optical microscope cannot go beyond 5,000 nanometers. SEM normally can go to 10 angstroms, and the TM go beyond 1 angstrom. So it depends upon what you have to measure. The three are very important. You have to do the three, okay? But it's not that one is more important than the other. You have to do the three. But the limit is the size of what you are seeing. And if you are going down in size, as Andy said, the high end becomes more and more important because you are talking about nanometers and only the TM can scan in those regions. Mm-hmm. Mm-hmm.
I know we touched on this already a little bit, but the next question had to do with the smaller microchips, the 1 nanometers being, did I say that right?
Mm-hmm.
Being more demanding. Do you want to expand on that at all, Miguel?
Well, okay, if I can quickly open my presentation and share it again very quickly. Look, this is the 1 nanometer chip that, no, I'm sorry, this is the one. This is the prototype that was published in a paper by Tanguay Semiconductors and MIT, okay? Look, if this, in order to be a one nanometer chip, the silicon has to be 1 millimeter, okay? 1 nanometer, I'm sorry. So if it cannot be 1.2, it cannot be 1 point, it has to be 1 nanometer, okay? And the contact has to be with a metal or with a semiconductor, depending on what. So you have to control very careful your contacts to have the proper. So they're very demanding because this is, let's say, in the 14 nanometer chip, then you have some margin of error, okay? Like, probably 1%, 2% of error, and that's okay. In this case, you cannot have that error, okay? And especially if you make it smaller, then you run into the problems of the quantum mechanics because then it will become what we call the physics a confined system, and then you will start to have other effects. So that's why they are so much more demanding than the 14 millimeters. And also let me just go back to what Andy said. Now the microchips are 3-dimensional, okay? So if you want to test, you have to test one layer. Andy probably mentioned what you mentioned, 20 or how many, Andy, layers? But anyway, you test the first layer, remove it, test the next, remove it, test the next, and that's extremely complex. Okay, if you don't do it correctly, then you screw up the complete analysis. And remember, quality control is to assure that the chip will work as predicted and will really be reliable to put it in a computer. And this cannot be done without the focus ion beam ion, the ion, the ion milling, okay? Not the ion, the plasma milling, okay? In which they produce a plasma gas, and the plasma really interacts very softly with the surface and removes atoms in a very controlled. Okay? So it has to remove the preparation of these samples. It has to be done with this system, not with the conventional FID. Okay, so that's why it's more demanding. I'm sorry to take too long.
It takes a while to explain it.
Mm-hmm.
It's not that easy to explain.
Mhm.
So what are advances in metrology that maybe are not widespread as of yet? Do you know of any trends or anything that might affect the semiconductor
What I
industry?
mentioned is, in my opinion, the two main advances in characterization are the four-dimensional STM, four-dimensional microscopy, and the plasma focus ion beam. They are still not widely used. At this point, they are being used in universities for research, not really being applied to the industry. But those are the next step. These two things. And one thing that we need to do is also use the TM to do more careful microanalysis, because what is used is called the secondary mass ion spectroscopy. It's a very large spot. So really you can prove the impurity because you are doping your system. You can prove it in a large scale. Now we will have to go to a smaller scale, and that has to be improved. That's an instrument that has to be improved. It has not been improved so far. That's more or less what I see in the future.
In our last conversations, Miguel, somebody brought up what is virtual metrology. Can you explain that?
Oh, okay. No, Mandy, Andy could.
Oh, sorry, Andy.
Maybe Carlo can explain that as well. So let me just make a start. So Carlo, you can chime in. So, Dr. Yakman talked about 2 nanometers, 1 nanometers. That is really advanced chip. Research right now is on research, but a few years later, it will be in manufacturing. But if you see overall the semiconductor industry, what are the most useful chips? Still is 40 nanometers, even 28 nanometers, pretty often utilized in the civilian side, right? So, the sensors, activators, and our home appliances, they don't need 1 nanometer, 2 nanometers. So what I'm trying to say is the vast majority of semiconductor manufacturing is those larger chips. So where is the challenge? The challenge is the metrology, the quality analysis. If you put a sample under microscopy and do analysis, it's a very time-consuming process. Of course, we'll do sampling, right? We're following the SPC and the standard. But the question is, how do we improve the efficiency, productivity of the quality control, the measurement side, right? So there is a concept called virtual metrology, which is already moving to the real production side. It's not just a research anymore. So basically, the idea is that instead of measure the sample, your product line, pick a sample and doing the measure under microscopy and measure it either manually or automatically, right? So virtual metrology, basically you install a number of sensors on your product line, right? It will monitor your whole manufacturing process from the silicon to wafer to die to packaging, all these process. It gathers data about your process, your product, and including some critical dimensions gathering those data. And then it uses artificial intelligence, data mining, and machine learning to monitor the process, do the analysis, and give you a prediction and give you a report, so that if there's any abnormal occurred, it will give you the warning message ahead of time. That can be done automatically. So, so that is that's basically the idea of virtual metrology. Of course, virtual metrology rely on your historical data, right? Anything you apply artificial intelligence, the power of artificial intelligence, your data set, right? So you have to have enough the historical data collection, so that the virtual metrology can compare the current production with the historical one. It's just like the large language model, right? The ChatGPT is smart because it has a huge data set, a training set to help it to predict the next word. Similarly for virtual metrology. So primarily it's based on artificial intelligence and data collection, sensor, smart sensors, and help with the quality control. So that's on the very high level explanation. Carlo, please.
Yeah, I was thinking maybe one of the biggest challenges for the new technologies is yield. As the devices shrink, we have a lot of problems related to actually the atoms inside the gate of the transistor. We have problems such as random dopant fluctuation. So depending on the number of impurities in your channel, you might have different threshold voltages. You might have a new set of problems and variability in your MOS transistors. So being able to characterize and understand exactly what is in your gate in the transistors extremely important. Maybe the best problem would be yield, to guarantee that all the transistors inside your microchip behave the same way. So this leads to one question that I was reading here. The 4D for this is something called tomography. So we can have a three-dimensional view of your device. And this tells us what impurities, for example, we might have in the channel. And with respect to virtual metrology, this is very useful for teaching, for example. Having a clean room is something very expensive. Many universities don't have it. The maintenance is extremely high. So being able to visualize process line or some advanced metrology equipment using virtual reality or augmented reality is very useful for training students.
Absolutely. I think, Hillary, do you have a question from the audience?
I do. So we had someone in the chat ask, could somebody explain the 4D or 4 dimensions of TEM?
Okay, what happens is that, of course, the 4 dimension is time, because you are rastering your sample, and then you are taking different times. So they call it 4D because you analyze the 3 dimensions plus the time, okay? The evolution with the time. And by the way, I have to say that in these microscopes, you can easily obtain 200,000 images in probably 1 hour. And therefore, the only way to analyze those is by machine learning, artificial intelligence. And that will help, because as you know, machine learning depends on the database, and the database has to be big, as Sandy said. And then in the future, it's going to be applied to this very small case. And what Carlos said will be the same thing. I mean, we have to do it by machine learning, not case by case. It will be impossible. Okay?
Looks like there's another question on the line. Would it ever make sense with measuring semiconductors for quality assurance to construct a digital twin to compare production units coming off the line?
That is a very good question. Actually, if you check the NIST website, NIST has a NOFO funding opportunity. And one of the big funding area is digital twin for metrology. So ideally, we are going to create a digital version for every metrology equipment, right? Expensive or not. Of course, the most expensive one, we do need to create a digital twin for that expensive one first. So ideally, so every measurement equipment will have a digital version. So when we do the virtual metrology, we can use digital twin to do that. And also for the whole overall quality control, the digital twin give you a quicker response and a more whole picture, general whole picture result. So, go back to the 4D issue, right? A lot of temporal property of your product will need that the fourth dimension. So that's why the powerful equipment can generate not only static property, and it can generate temporary property with a time variable into it. So that is very interesting. Thank you for your question about digital twin. One thing we are doing here at NAU is we're trying to create, first start with virtual reality and then move to augmented reality. Because augmented reality is even more challenging than virtual reality. So we're going to use it for training. And then later on, if we can implement digital twin for every metrology equipment, and then it can be really used in the production line, not just for training purpose. Thank you.
There's one more advantage. If you have a digital twin, you can train machine learning models to do anomaly detection, right? So when you are doing inspection of your microchips, your machine model can detect something that is off the curve. Yeah.
Thanks, Carlo. My actual last question was about AR, VR, Andy, and you you went ahead and answered it. So thank you very much. I just wanted to take the time just to mention that, NAU is very committed to this area of quality and, starting at all different levels, be it from research in our metrology research and teaching lab, to our certifications, to our degrees, to our registered apprenticeship programs. And also we're opening training centers in Phoenix, the North Valley campus, like Andy mentioned, as well as working with other government organizational partners to get more opportunities out there for training. And offering workshops as well, like the quality control, where you can actually have hands-on time with the TEM. We want to be the school that everyone thinks of when they think of metrology. So that's NAU, they're synonymous. And I just wanted to add that in for kind of a conclusion in a way. And Hillary, I don't...
Something?
Oh, go ahead.
But the other thing that's important is, of course, industry will use very well developed techniques. Okay, they cannot afford to use something which is testing. And then the opportunity, on the other hand, in the universities, we have to do research, or students have to produce papers and things. So that really gives a great opportunity to develop the techniques. Okay, once that we are in contact with the industry, I think we can learn what need to be developed of the technique. Like just Carlo mentioned, it's a technique that doesn't exist, but then the research might be able to develop. So that's the great value, besides of education, is research to advance what eventually will become part of the production line. Thank you. So did you see NAU as your research partner?
Thank you so much to all of you, to Dr. Dacuna and Dr. Wong and Dr. Jose Yakiman. We really appreciate you taking the time out this evening to discuss this topic with us. It's a very hot topic right now, as you mentioned, because Arizona has kind of become the hub for this. So we really appreciate it. Is there anyone on the call that has an additional question for our team?
Yeah, I've got a quick question. My company is just about to spend $20K with EAG Labs, and I'm wondering if the lab at NAU is ready to take outside jobs for doing a fib analysis. It'd be a cross section and a fib analysis.
Yes, Dr. Yakiman is an expert in the area. I mean, we will be happy to do those kind of things. Miguel, if you want to add anything.
No,
Okay, great.
absolutely. We're willing to work with the industry, and that's what will distinguish NAU from other places. I don't want to mention other universities in the state, but sometimes the commitment with the industry is not very strong. We want to build research very committed for service and training and research with the industry. So definitely we will do that.
Or if you have any, let's say, you write a grant proposal on the SIG grant and you need an education partner, we'll be happy to be that, provide workforce development for you or doing R&D with you. So, you know, NAU is compared with ASU. I mean, the engineering college, we are small. I mean, ASU has more than 30,000 engineering students, engineering college alone, right? And we have only 3,200 students at this point. However, we are very flexible. We are nimble. We can work with you for grant, for research or development, or we can do a targeted training with you. And together, I think we can make a difference because Arizona is becoming a semiconductor hub, right? Now, the question is, how do we make sure that all those investments will have a return, right? I mean, Biden would like to have all the manufacturing back to this nation. However, I talked to many company and asking what kind of workforce, what kind of talent they need. Well, it turned out that they are not only need engineers, they need technicians. Probably if you start a new fab, probably only 40% engineers. The rest are different kind of technician. You need a machinery people, you need equipment technician, process technician. So technician is really a key. However, traditionally, university is not producing technicians. It is a community college. But many students actually do not even go to community college. As I said, I mean, 38% of high school graduates, they never go to have an advanced degree. So we need working together. I mean, reach out to that population, give them training, education, give them a skill set right to the industry need, meet industry need. So if you're interested in working with NAU, please contact us. I mean, I saw Hillary mention that to become a senior member of ASQ, one way is that you teach for university for 2 years, right? Please let me know if you have that interest, okay? You can either do it voluntarily or I can pay you. I mean, you're part-time or adjunct professor teaching for us, and we can pay you. So so that is a win-win because our student need definitely those people from industry with tons of experience, real-world experience, and for you, of course, you can identify talents and recruit best students to your company. Thank you.
Andy, there is a question about in the chat. Maybe you can answer it about the macro metrology.
Yep, someone was asking, the question is, I know it may be a bit out of the scope of tonight's topic, but is NAU working on metrology for macro level work?
Oh, Dave, could you explain what exactly is the macro level work? And you're talking about a non-semiconductor or microelectronics or focus on, for instance, mechanical engineering side of traditional critical dimension at a large scale.
Traditional metrology,
Yeah.
CMMs, hard measurements
Yeah, that's great.
on things that are physical in nature that aren't on the microscopic level.
You know, interestingly, today I have an industry come here to demonstrate their tools, time to sell to us. I invite our faculty come here. You know, who comes the most? Which department? That's mechanical engineering department faculty. So yes, to answer your question is yes, we are going to do metrology for everything. Currently, the grant, of course, is focused on semiconductor and microelectronics. However, you have to learn the basic GDT, critical dimension, and those, and move forward to the small scale. The difference between semiconductor and the general macro level metrology is the scale, right? You're talking about a nanoscale, the atom level analysis. That's the difference. But the general principle is the same. We want to have a quality, right? How do we maintain the quality, right? So the metrology is the science of measurement. How do we really provide precise, accurate measurement, right? That's the key. So answer your question, yes, we are starting with macro level and move to micro level, from the larger scale to the nanoscale and atomic scale.
Yeah, okay. That's good. Yeah. Looking for skill sets in metrology, but on a larger scale. So maybe there are some things you can do, help us out with.
Great, we'll be happy to work with you. You know, our neighbor, WL Gore, they need someone, you know, focus on mechanical biology, you know, the medical devices, right? So
Yeah.
that's
It's
really
very
not a
important for medical
semiconductor.
devices, sure.
Yeah, right.
It's critical for medical devices. Mhm.
Yeah, so West Pharma, for instance, they reach out to us because medical devices require much more regulation, standard, and I mean, this group know much better than me. I mean, this is the macro level quality control is equally important. So we'll do it. Certainly, we will do it.
Do we have any other questions for our panelists this evening? All right, look at the chat. Okay. I'm not seeing any come through. So I just want to thank all of our panelists and our moderator, Lauren, this evening for joining us. This is, like I said earlier, this is a very hot topic in Arizona right now, and it's very timely. And we do appreciate you joining our meeting this evening to discuss it further. Thank you all so much.
Well, on behalf of the NAU Metrology Group, I'd like to thank you, Hillary, and thank the ASQ Phoenix chapter to offer this opportunity for us. So finally, I really want to invite everyone, please contact us, contact Lauren, and if you have any idea or any kind of opportunity for us to working together, you know, educate our next generation, make sure that our industry not only have a good productivity, but very high quality. I mean, this is a really important topic. As I mentioned that traditional engineering education emphasizes design, but not really. I think we should have both design and quality. So thank you so much.
Thank you.
Thank you. We do have just a couple more announcements this evening for folks that would like to hang on the line.
Okay.
Let me bring up my presentation.